So last week we started about heat for solids and the liquids, and we derive it, we logically explain it, how this MC delta T equation can be derived logically. But we only can use it for solids and liquids. Today we will try to apply heat for gases. And from school, you know that for gases we use different equation, and we call it first law of thermodynamics. Before starting first law of thermodynamics, let me explain why we cannot use MC delta T for gases. Why we cannot use same equation for gases. Let's take again simple example. This is iron, for example, basically solid. And we have a liquid, for example, water. If you start heating these two substances, two objects, what will happen? If you observe, if you watch it carefully, temperature will increase. For iron, for water, temperature increases, but mass will be constant for both. Also, volume will be constant. If you pay attention, if you start heating, for example, water, volume will be always same. Just only temperature will be increasing from 20 degree to 50, 60, 100. Same for iron, for solids. Volume will be same, it will not change. 1 meter cube, it will be still 1 meter cube. But for gases, it's a bit different. Let's say air. When you heat air, temperature increases. At the same time, volume can change. It's not constant anymore. That's why for gas, you cannot use this equation anymore. Because volume changes, it's not constant anymore. It's simple to observe from daily life. For example, balloon, yes? If you bring it to the sunny day, its volume will be bigger. If you bring it into the refrigerator, it will shrink, volume decreases. It's very easy to absorb in daily lives. Here we will not do that experiments. So basically now we know that we cannot use MC delta T for gases. So scientists, researchers did some experiments and they came up with this kind of equations. I will write it directly. Basically this is not MC delta T, that's all. So we call it first law of thermodynamics. This is a heat. This is a work. This is a internal energy. Internal energy. So we said that volume changes, temperature changes. Basically, volume depends on work. If volume changes, it means work is changing. And the second physical parameter for gas, it was temperature. If you change the temperature, internal energy will change. For solid and the liquid, only temperature. Heat depends only on temperature, basically. That's why in MC delta equation we have a temperature. Here, logically, for gases, in the equation you should have volume, something that depends on volume, and also something that depends on temperature. Basically, for volume is work, temperature is internal energy. So let's start with work. Work actually equal to integral of small work. Integral of small work. And this delta W, small work basically for small time, equal to pressure times small delta V. This is a main formula, main equation for the work. You should remember, this is the original equation for work. Of course, we can apply it for isobaric process, we can apply it for isovolumetric process, we can apply it for isothermal process, etc. But they are, all these iso processes comes from this original equation, P delta V. P delta V. Now let's start with isobaric process. For example, we have isobaric process, how we can calculate its work. First one, isobaric process, pressure is constant. We need to calculate work, which is P delta V. In isobaric process, we know that this P is constant, basically just number. You know, from mass, integral of this kind of equation is we can take constant number outside, yes? Just delta V. Integral of delta V. This is very similar to the what? Integral of delta X, which is XS. Same here. Integral of delta V will be equal to just V. From V1 to V2. So, for isobaric process, we have this kind of equation. V2 final volume, V1 initial volume. So work for isobaric process equal to P delta V. This big delta means change. O V final minus V initial. Be careful. You need to just remember this is only for isobaric process. Now let's continue. Second process, volume constant. Volume constant. This part is very simple. Volume is not changing. Here, for this equation, this part is equal to 0 basically. It's not changing. Delta means change. But for isovolumetric process, volume is constant. It's not changing. So basically, you will get zero work for isovolumetric process. Basically, first law of thermodynamics for the V constant process will be equal to just Q equal to delta U, because work equal to 0, because volume is not changing. It's constant. Isothermal process, when we have a constant temperature. So work equal to P delta B. This part is mass. In this kind of process, volume changes. It's not constant. At the same time, pressure changes. It's also not constant. So basically, this symbol is not constant. If you remember, for isobaric process, it was constant, just numbers. That's why we took it outside of the integral. But for this case, it's not constant number. It's changing. It's changing. It means we should find its formula, equation for P. We should find P, equation of P in terms of volume. Only in that case you can integral the equation. So, for isothermal process, P initial, V initial will be equal to P times V at any time. At any time. Basically, from here, pressure at any time equal to initial pressure times initial volume divided by volume at this moment. It means we can use this equation for our work. So now we can replace pressure P1 V1 over V times delta V. Now it becomes very simple equation. Initial pressure and initial volume usually will be given. So it's a given number, constant number. It means we can take it out of the integral. So P1 V1, here we have a delta V, V. So now we can simply integrate this equation. Here we have a delta V, here we have a V. So same variable. So P1 V1 integral of this part will be equal to ln V. V1 is initial volume to the final volume. So at the end we will get this kind of equation, ln V2 over V1. If you continue this one, you will end up with this equation. P1 V1, basically it's equal to nRT1. You can also write it in this form, T1 or just T because temperature is constant, V2 over V1. So this is the work for isothermal process. Now let's explain the same explanations in terms of graphs. So work is P delta V. So basically we have a PV graph for isobaric process. This is initial point, final point. As you know, work will be equal to P V2 V final minus V initial, which is basically this area. This part equal to P, this part equal to V2 minus V1. So P times V2 minus V1 will be equal to area of this part. It means we can conclude that if you have a PV graph, area under the line will be equal to work. Okay, let's check it. So we just checked it for the isobaric process. Let's do it also for the isovolumetric process. Let's draw PV graph, but here we have a V constant process. Initial point, final point, this is a direction. So in the first case, we said that area under the line equal to work. Let's check it for this case. Volume is constant, so area under this line is basically this one, yes? Zero, which is zero basically. And we know that work for V constant process equal to zero. It means logic is correct. Okay, let's check it again for the last process, isothermal process. For isothermal process, this is a line, initial point, let's say final point, or vice versa. Let's check what is the area under this line. Area under this line in terms of mass, in terms of geometry, is equal to this one, y delta x. In terms of mass, I'm trying to explain. In the mass, this is a y-axis, this is a horizontal axis. In our case, it will be P delta V, which is totally same as our physical equation, P delta V, which is at the end you will get this equation. It means this area indeed equal to the work, only if you have a PV graph. So first of all, let's draw. So here we have our cylinder, here we have a piston, here we have a gas, and initial temperature T1, this is initial temperature. Let's find at this case pressure of the gas. So very simple. Here we have a atmospheric pressure which will create this kind of force. Downward we have a weight of the piston. Upward we have a force created by the gas, inside gas. So it means, and at the beginning piston was at rest, so P0S plus mg equal to PS. Basically total force acting on the piston equal to 0. From here we can find pressure of the gas, which is P0 plus mg over S. We can calculate it quickly. Atmospheric pressure approximately 10 to the power of 5 Pascal plus m, mass of the piston 8,000 grams, which is 8 kilogram, times gravity approximately 10, area 5 centimeter square. In terms of meter it will be negative 4. So at the end answer will be, so initial pressure of the gas equal to 2.6 10 to the power of 5 pascals, and this pressure is constant. It was given already in the problem. So someone is heating this gas, temperature is increasing, pressure is constant, so this piston will go upward because volume increases. So this piston will move somewhere to this point. This will be initial volume, V1, this will be final volume. And we know that for isobaric process, which is our case, work equal to pressure times final volume minus initial volume. We already know value for the P. We only don't know value for final volume and the initial volume. But it's that problem. Let me write the same equation in this form. This is basically final pressure. This is initial pressure, which is equal to initial pressure because it's constant. Yes? And actually this part equal to nRT2, final temperature. This one equal to nRT1. It means work, this one actually equal to nRT2 minus nRT1, basically T2 minus T1. So we can rewrite this one in different form basically. That's all. It means so in this equation everything is given. It means we don't need to calculate pressure. But it doesn't mean it's incorrect. It's not wrong. It's correct. But we cannot use this value basically. But it doesn't mean it's wrong. Okay. N 0.2 moles. R is constant number 831. T final is, actually it should be in kelvins. But since this is the difference, there is no need to convert into Kelvin. 300 minus 20. And the final answer will be work equal to approximately 465 joules. So let's solve this problem. Let's draw PV graph, because we know PV graph under the line gives us work. Initial point is here, VI and PI. After some time, volume increases by 3, pressure also increases by 3. So now, and also we know that pressure depends on volume. It's proportional to the volume, directly proportional. It means P equal to KV. K is constant number, but it's not important. The important thing, this is a straight line. This is a straight line. Initial point is here, final point is here. So we need to just add these 2 points. This is our line. This is the direction. And this area will be equal to work. And it should be positive because volume is increasing, basically. And there are several ways of finding volume area of this figure. Let me use this method. Rectangle. Area of this rectangle equal to this side, which is pi, times this side, which is 2vi, will be equal to 2pi vi. Area of this right triangle equal to this side, which is 2pi, times this side, which is 2vi, divide by 2, because this is a right triangle. So this area will equal to also 2pvi. So total area equal to this plus this, which is work for P initial times V initial. This is answer for the first part. Let's come to the second part, B. How is the temperature of the gas related to its volume during this process? So basically we should find temperature in terms of volume. So now let's find this relationship. We know that P initial, V initial equal to RT initial. And we know that pressure equal to constant number times V, because this is the definition of directly proportional. So initial basically K V initial square equal to RT initial, basically T initial equal to K over R V initial square. So this part is constant number. So temperature depends on square of volume. So basically it means if you increase volume by 2, temperature increases by 4. If you increase volume by 3, temperature increases by 9, because temperature directly proportional to the square of the volume.